Welcome to the problem-solving session for Chapter 35. Let's begin with question 1. Here, the question says, when you're driving at night, why is it more difficult to see the roadway in front of you when the road is wet? Well, the answer here is that the layer of water on the surface will produce a more specular reflection. And if you recall, the two types of reflection, specular and diffuse, in the case of diffuse, the reflection of light moves in every direction, illuminating the background. In the case of specular reflection, however, light comes in a very direct direction, and it reflects in that same direction. Diffuse reflection occurring, see, these would be all the beams of light from your headlight, for example, and all of these travel along the same direction, and there's no illumination of the background. Next question. Two plane mirrors are shown separated by 120 degrees. If a ray of light strikes mirror 1 at 65 degrees, at what angle theta does it leave the second mirror? And here, the angle between the two mirrors is 120. Please recall that when the angle was 90 degrees, then we got retroreflection. So in other words, this ray would, if this angle was 90 degrees, this ray would return along the same direction as the incident ray. But since that isn't the case, we go ahead using the law of reflection. This is our theta 1, so we know this angle is 65 degrees. And because this is 90 degrees, then it must be that this angle is 25 degrees. But since this describes a triangle, and the triangle must have the sum of its angles equal to 180, we take 25 plus 120, we subtract that from 180, and we get 35 degrees. Well, again, this is 90 degrees, so this must be 55, and therefore the reflected ray must exit at 55 degrees to the normal. Next question. A laser in a compact disc generates light that has a wavelength of 780 nanometers when it's traveling in air. The plastic of the CD, however, has an index of refraction of 1.55. Find the following quantities below once the light enters the CD. Okay, well, when it enters the CD, the speed is going to be reduced by the value of n. And if we take 2.99 e to the 8 meters per second, and we divide it by 1.55, we get a value of 1.93 e to the 8 meters per second. Oops. The wavelength is also reduced by the value of n. And again, here we take 780 nanometers, divide by 1.55. For some reason, the writing is not very good today. We get a wavelength of 503 nanometers. And last, the frequency of the light, well, remember that it's going to be unchanged, whether we are in the plastic of the CD or we're in the air. And in either way, we obtain it as the ratio of speed over wavelength. So speed of light over wavelength of light in vacuum, or speed of light reduced in the plastic divided by the wavelength of the light in the plastic. And in both cases, we get 3.83 e to the 14 hertz. In other words, unchanged, unaffected by whether the light is traveling in the air or the plastic. Next question. Here we are told that a beam of light of wavelength 550 nanometers travels in air and reaches an interface where there is a transparent material. So this tells us that air is medium 1 and N1 is equal to 1. The incident beam makes an angle. Here Q is actually theta 1. Unfortunately, the software doesn't recognize Greek letters. So theta 1 is 40 degrees with the normal. Theta 2, the refracted ray, makes an angle of 26 degrees with the normal. And we're asked to determine the index of refraction of the transparent material. Well, we can use Snell's law. N2 sine of theta 2 is equal to N1 times the sine of theta 1. Solving for N2, N2 will be equal to 1, the value of N1, times the sine of 40 degrees, that's theta 1, divided by the sine of 26 degrees, which is theta 2. And this gives us a value of 1.47. And by the way, if you've ever noticed a CD, when you hold it up to the light, will actually produce a rainbow of colors, and that is because the CD in a way similar to the prism acts to separate out the wavelengths, and each wavelength has a unique value of N. Okay, next question. A beam of light is traveling through diamond and reaches the diamond air interface. The angle of incidence, here of course, angle of incidence means theta 1, okay, and remember we're traveling from diamond reaching air, which means that diamond will be N1, and in this case air will be N2. Okay, so what is the critical angle for light moving through diamond to air? So in this case, if you recall, the critical angle, theta critical, is equal to the inverse sine of N2 over N1. And just a quick reminder of where this came from, the fact that N1 sine of theta critical is equal to N2 times the sine of 90 degrees, which is equal to 1. So that's how we get this expression. So in the first case, we're told that N2 is air, N1 is diamond, so theta critical is equal to the inverse sine of 1 divided by 2.42, the index of refraction for diamond. And this gives us a critical angle of 24.4 degrees. Well, the next question says, will this incident beam, the one that comes in at 28 degrees to the normal, enter into the air, in other words, transmit to the air, or be totally internally reflected? And if you recall, the condition for total internal reflection occurs when theta 1 is greater than the critical angle. In this case, we get total internal reflection. On the other hand, when theta 1 is less than the critical angle, we get transmission. In other words, the ray will transmit and refract at the second media, which in this case would have been air. So because our theta 1 is 28 degrees, theta critical is 24.4. In case A, we're going to get total internal reflection. Now, in the second case, we are told to repeat the calculation in the situation where the light is traveling in the diamond but reaches the diamond water interface. Well, water has a value N2, where the light's going to, of 1.33 divided by 2.42. And this time we're going to get a critical angle which is bigger than 24.4, and in fact is 33.3 degrees. Well, this is a situation where theta 1 now, 28 degrees, we still have the same theta 1, is actually less than the critical angle. So in case B, we're going to get transmission. Last question. Here we're told that a beam of light is a mixture of 3 wavelengths, red, green, and violet. It is traveling within a prism that is surrounded by air. The index of refraction is given for each of the wavelengths. So notice here now, because the prism plays the role in separating out all the wavelengths, each wavelength has its own unique index of refraction. And the question is, which of the colors of light will this gentleman right here observe? Now, he is on the other end of the prism, so he can only see the colors which are being transmitted, in other words, refracted. He cannot see the colors which undergo total internal reflection. And here again, let's just draw a normal so you can see that in all cases, theta 1 is equal to 45 degrees. So our task is to obtain the critical angle for each of the different colors, the wavelengths, and then ask ourselves, if theta 1, once again, is greater than the critical angle, then we say total internal reflection. And what that means is that the man the man won't see these colors because he can only see the ones that are transmitted. So when theta 1 is less than the critical angle, then we get refraction, and what that means is that the man will see. So for us, any value of critical angle which is less than 45 degrees means that our man will see the color. So let's go ahead and calculate the critical angle for each of the wavelengths. Theta critical for red is equal to the inverse sine, and remember it's surrounded by air, so in all cases 1 is in the numerator, divided by 1.43, and that gives us a value of 44.4 degrees. Question, is 45 degrees less than 44? The answer is no, so the man will not see this color. Okay, theta critical for the color green now. Inverse sine of 1 divided by 1.4. This gives us a value of 45.6. Question, is 45 degrees less than theta critical? Yes. So the man will see this color. Last, is theta critical, for violet, last one, inverse sine of 1 divided by 1.37. The answer, 46.9. Is 45 degrees less than 46.9? The answer is yes, so the man will see this color as well. Well, this concludes the problem solving session for chapter 35. Until next time,